This is Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to investigate and model Faraday's law, Lenz's law, induced EMF, and magnetic force. The model in this lab was that we modeled the aluminum tube in the magnet using glow script. Faraday's law, Lenz's law, induced EMF, magnetic force, gravity, magnetic force on the wire, and the magnetic field of a dipole are all relevant to this lab. The main result is that the magnet took 1.18 seconds to pass through the tube in the experiment, and it took 1.43 seconds to pass through the tube in the model. Some fundamental physical principles in this lab include Faraday's law, which states that the induced EMF is equal to the line integral of the vector electric field dot product, the dl vector, and this is also equal to the negative derivative of the magnetic flux over time. Lenz's law states that a changing magnetic flux through a loop induces an EMF and therefore a current in the loop that produces a magnetic field opposite to the change in flux. The induced EMF is related to this. The force of gravity is equal to the mass times g, and the magnetic force on a wire is equal to the current times the cross product of delta L vector times the external magnetic field vector. The magnetic field of a dipole is equal to mu naught over 4 pi times 1 over r cubed times 3 times the dot product of mu and r hat times r hat minus mu. And in this case, mu is the magnetic dipole moment of the magnet. In the experiment, the system was the aluminum foil roll in the magnet, and the surroundings were the Earth and the universe. The initial conditions are that the magnetic north pole is pointing down, held at rest, and the roll is also held at rest below the magnet. The procedures of the experiment are that we first label the north side of the magnet, which was determined using a magnetometer on our phone. We acquired a roll of aluminum foil with a thickness greater than 1 centimeter. We took a video of someone dropping the magnet and of the magnet falling through and out of the roll. By stopping the video, we determined how much time it took for the magnet to enter and leave the roll. We then repeated steps 2 to 4 5 times in order to have 5 time measurements and take the average of the times. In our code, we first put in all the parameters relating to the geometry of the tube. We then put the mass and the magnetic dipole moment found in Lab 3 into our code. Then we created a function to calculate the magnetic field at a point when given the magnetic dipole moment in a position vector. We then created a function to calculate the derivative of the flux with respect to time. The force of gravity on the magnet and the magnetic force on the magnet, or the net force, the derivative of the flux with respect to time, the current in the ring, the velocity of the magnet, and the position of the magnet were calculated iteratively, and the position and velocity were updated. So first of all, we cannot use a Faraday's tube because the tube itself would cause a magnetic force in the x direction, so the magnet would be attracted to the tube, stick to it, and not fall. Also, the magnet falls slower when it passes through the tube compared to when it falls in free space. A similarity between the model and the experiment is that the model itself models the experiment to a good extent, but a difference is that the magnet does not fall perfectly straight through the roll, so the x direction is changing as well, which affects the flux. Some sources of error in this lab could include that the magnet was hitting the sides of the roll, so any forces or energy loss associated with this was not accounted for. Also, the magnet sometimes passed through the tube at an angle, which directly affects the magnetic flux. So this section covers the results and the interpretation of the simulation. In order for the magnet to be slowed down, the red current must produce a magnetic field up, and the blue current must produce a magnetic field down. Therefore, the current in red is counterclockwise and the blue is clockwise. If we flip the magnet around, everything stays the same except for the direction of the currents. They would now flow in the opposite direction. So the results of the experiment was that the magnet fell through it in 1.18 seconds, and in the model, the magnet passed through it in 1.43 seconds. They differ by about 0.2 seconds. The model could account for n hat and til of the magnet in order to be more accurate, and it could also consider the thickness of the aluminum foil itself, because heavy-duty aluminum foil is thicker than a light one. This is our velocity versus time graph acquired in the model. The shape of the graph indicates that the velocity of the magnet is increasing or accelerating, and then it reaches terminal velocity when it enters the roll, and when it comes back out, it accelerates down again. This implies that the force of gravity down and the magnetic force up are equal and opposite in the roll. As the resistivity approaches 0, the current approaches a very, very large number because dividing by a small number does this. Therefore, the magnetic force acting up on the magnet would be very large, and the magnet would shoot up. If there were holes or slits cut into the tube, some of the rings would be open and no current would flow through them, and they wouldn't produce a magnetic force, or at least a strong one. Therefore, the magnetic force pushing the magnet up would decrease, and the magnet would fall faster. Thank you and have a great day.